Alright, so in this video we're going to jump into the fundamental theorem of calculus, part 2. Okay, so some people call this the second fundamental theorem. Some people, like myself, call it part 2. Doesn't really matter. And really our goal today is to answer two questions. Our first question is, how do you take the derivative of a function that is given to you as an integral, that is defined as an integral? Our second question is, what does it mean to define a function as an integral? Okay, so we're going to start with question 1. Okay, so we're going to call a function g of x, and we're going to define it with an integral. We're going to say it's the integral from a to x. Sure. So we're going to use something that's not just a and b anymore. That's what's going to be new today. Of f of t dt. Okay? And we're asking ourselves, how do we derive g? Like, what is g prime of x? Okay, so that's what we're going to try to do here. So let's kind of think to ourselves what g of x really is here. So we're remembering our definition of an integral. Just got spots everywhere, don't I? So we know that g of x is this integral from a to x, f of t dt, which means it is the antiderivative of f, so our notation would tell us capital F of t evaluated from a to x. And so therefore we could expand this and say that means it's f of x. This is the fundamental theorem of calculus we've already discussed with the evaluation, minus f of a. Okay, so all of that is what we already know how to do coming into this lesson. So now we want to derive it. So if we're finding g prime of x, that means we're finding the derivative with respect to x of the antiderivative of the function at x minus the antiderivative of the function at a. So I'm going to plug that in here. All right. So let's think about what that would look like. So if I take the derivative of oh my gosh, I'm just erasing stuff. What is going on? Of the antiderivative. I'm taking the derivative of the antiderivative. Well, if you think about that, the derivative of your antiderivative, that's just your original function right back. So what I'm going to end up getting is simply f of x. Now if we think a little bit more here, f of a, that's just a value. That's a constant, right? That's just some number that I'm plugging into the antiderivative and it's giving me a value. So when I derive it, it simply becomes 0. So yes, all this fun work for us to realize that this whole time, the derivative of this function defined as an integral is simply f of x. Alright, so our second fundamental theorem of calculus, or if you want to call it part 2, again, it doesn't really matter to me, is going to state the following. And it says, if g of x is defined as an integral from some value to x of a function f of t dt, then the derivative of that function simply gives us the function we were taking the integral back. So basically we're deriving and then we're taking the integral and then we're deriving, and those two things kind of undo each other. So essentially we just get that original function right back. It's just that we're plugging in whatever it's defined as. Another way you might see this is we sometimes write it as you're taking the derivative with respect to x of some integral from a to x of f of t dt. And when we do that, again, what we're really doing here is we're taking whatever this is and we're simply going to plug it in. And we're going to get f of x. Okay? So I know this seems kind of weird. It's a lot of notation understanding more than anything, but the actual math is pretty straightforward and actually pretty easy. So let's just jump into some examples here. Okay, we'll keep this right here where we can see it. So example 1 is g of x equals the integral from 0 to x of 1 over t squared plus 1 dt, and they want you to find g prime of x. Okay, so I'm going to kind of break down this first one again into all the steps, and then we're going to start kind of doing it the fast way using that theorem we just wrote down. So essentially what we're doing here is we're taking the derivative with respect to x of this function from 0 to x. I'm going to call it f of t because I don't feel like, here's the thing, we don't really need to find the antiderivative of this because we're going to end up deriving it. So I like to just call them f in my work, so I'm not doing extra work here. Okay, and when we find the derivative of that, we're really finding the derivative of the antiderivative of the function at x minus the antiderivative of the function at 0. Well, the derivative of the antiderivative simply gives me f of x, and the derivative of some constant gives me 0. And so I'm just left with f of x, which means I'm essentially taking x and plugging it in for t, right? And so we're going to end up getting f of x, we'll say g prime of x equals my function, my function evaluated at x, so 1 over x squared plus 1. My goal is for you guys to be able to go straight from here to this. Like, we can go straight there. This is, again, just explaining the theorem. But we're essentially just plugging in the variable. That's all you got to do. So let's try another one. Example 2. All right. So this one I'm going to say find the derivative with respect to x of the integral from 3 to x of 5t cubed minus 4t plus 1 dt. All right, so let's try this shortcut here, because every single time what's going to happen, every single time, no matter what my function is, I'm going to take the derivative of the antiderivative, get that function right back with x in it, and no matter what this number is, it's always going to go to 0. So we're just going to skip straight to plugging x in, and that being our answer. Okay, so for this one, I'm simply taking x and I'm plugging it in, right, everywhere I see a variable. And that's about it. So for this one, I'm simply going to get 5x cubed minus 4x plus 1. And that's it, my friends. You want to do another one? Let's try another one. All right, example 3. What's example 3 going to be? Let's say, let's try something different, just slightly. If g of x equals 6 to x squared of some function. find g prime of x. So the difference with this question and the ones we've done so far is it's not just an x now. Now I'm plugging in kind of a whole function, right? I mean, x is a function, but he's special, and you'll see why. So let's try this one out. So I'm going to show more steps for this one again, since it's a little bit different. All right, so we have g of x equals this integral. So that means that g of x is this. Okay, so using our fundamental theorem, we know that means we're evaluating the antiderivative function from 6 to x squared. And so this means that we're going to get f of x squared minus f of 6. Oops, f of 6. So now when I take the derivative here, right, when I find g prime of x, I'm finding the derivative of the antiderivative, which again just gives me back the function I started with, f. And that's all we were calling it. We didn't have a more specific thing here. So we're going to get f of x squared, but then we're going to use the chain rule. We just took the derivative of the outside, so now we have to multiply by the derivative of the inside. Oh yeah, you thought you had escaped it, but it's still here. Luckily, this part is still true, right? When I derive something that's a constant, I'm still going to get a 0. So this means the most we can say about the derivative, not knowing what f is, the derivative of g of x is f of x squared times 2x. So yes, now we're going to have basically still pretty easy problems, but the chain rule will be involved. So that's where that comes from, right? All right, let's try another example here. What is this, 4? Wait, was it 4? Yeah, example 4. All right, so let's try one with these chain rules. Let's see what that's like. So find d dx of a function that goes from 1 to 2x of t squared plus 3 dt. All right, so let's try our trick where we know we're just plugging this in for the variable. Okay, so let's just start with that. So we're going to get, what would that be? That would be 2x squared plus 3. But now we also have times the chain rule, so the derivative only of this part right here. So I'm going to do that part in purple so we can kind of see it. Well, no, I liked it in red because we used a red arrow. So times 2 would be the chain rule part of it, right? So this part's the same, I'm just plugging it straight in. And then I do the chain rule of whatever it was that was plugged in. I do not do the chain rule of the entire function, okay? So that's the only thing that gets a little twisted around here. So again, the reason we're able to do this, I'm just going to remind you, we're really finding the derivative of the antiderivative at 2x minus the antiderivative at 1. And when we do that, we get the derivative of the antiderivative at 2x times the derivative of the inside minus 0. And that's just going to give us what we wrote right here. So let's clean this up real quick, and we're going to get, let's see, 2x squared is really going to be 4x squared. And then we're going to multiply that by a 2. So we should get 8x squared plus 6. All right, let's try even another example. Okay, example 5. So take the derivative with respect to x. Ooh, we're going from g of x to f of x of h of t dt. Oh, that looks fun. All right, so let's try our trick again. So what we're really doing is well, maybe let's not try the trick because this one's kind of crazy looking. So now we have a function and a function on either end. So let's think about what this would be. It would be the derivative of our fundamental theorem would say find the antiderivative of this function evaluated from g of x to f of x. All right, so we're finding the derivative of that. So that's going to be h of f of x minus h of g of x. Okay, so now let's take the derivative of each one. And you know what? I'm going to use colors for f and g to make this a little bit less crazy. F of x and g of x. All right. Wait, no, we wanted that gone. All right, so now we're going to take the derivative. So you know how this works. We take the derivative of the outside, and the derivative of the antiderivative just gives me my regular h back of f of x times the derivative of the inside, which would be f prime of x, minus derivative of capital H is regular lowercase h of g of x times the derivative of, nope, we're using purple, times the derivative of g of x. And that, my friends, is another kind of property we're going to use. Okay, so I'm going to call this the second fundamental theorem of calculus. Extended. So it's kind of a part 2 of a part 2, not to get crazy, but it's kind of what we're doing right now. And it's going to state that if we're taking the derivative with respect to x of some function like the one we just did, we're basically just rewriting what we just did, just more formally. And I switched around some of the letters. So I put h and g on the integral because we normally use f for our function. Then we're just doing a lot of the chain rule. And actually, this looks really familiar because it's kind of like first. No, it's still just a chain rule. No first, you last. I don't need to get crazy here. Times g prime of x minus f of h of x times h prime of x. Whoa, let me try that again. H prime of x. All right, so that's, oh, wait, where did my closing bracket go? I missed it somewhere. Oh, it went right here. Might be. All right, so basically we're just doing the chain rule 2 times now because we don't just have a constant for this second one. Like this isn't just going to 0 anymore. Other than that, it's exactly the same as what we've just done. So let's try it out. What are we on now? 6? Yeah. All right. Example 6. Okay, let's see here. So find derivative with respect to x of the integral that goes from x squared to 2x of f of t dt. Okay, so this is just going to be the derivative with respect to x of the antiderivative function evaluated from, well, let's do this, evaluated from, and I'm going to use colors here. I'll use 2x as green and x squared as purple. All right, so that means I'm really finding the derivative of f of 2x minus f of x squared. All right. So the derivative of the antiderivative simply gives me f of, 2x. And then I have to take the derivative of the inside, which would be times 2, minus regular f of x squared, that's the derivative of the outside, times the derivative of the inside. Okay? And that's really about the best we can do, not knowing what the function f is. All right, let's do one more of these. So we're going to have the example 7 that says let g of x equal 6x to 4x squared of the square root 1 plus t to the 4 dt. Find g prime of x. All right, so let's try our trick here where we're not writing out all of the actual fundamental theorem, but we can kind of just use our theorems where we've just covered the part 2s. So they're going to tell me that I plug the first one in for t. So let's see, I'll get the square root of 1 plus plugging in a 4x squared. And then that's raised to the 4th. Then I need to multiply by the derivative of the inside, which would be 8x, minus the square root of, now I'm going to plug in a 6x, so I'll get 1 plus 6x raised to the 4th, times the derivative of the inside. And you know what? I guess we can clean it up a little. Alright, so we'll bring the 8x out front. 4x squared to the 4th. Ooh, I don't know what 4th is. Alright, it's 256. I cheated. And then that becomes x to the 8 minus the square root of 1 plus 6 to the 4th is beautiful as well. That's going to be 1,296 x to the 4, and I guess we can bring that 6 out front. And that's as much as you would definitely want to do on that one. All right, but this is kind of one way we're going to use the second fundamental theorem, or the part 2. Now, if we go back here to the beginning, this second question we will address in class, and it says, what does it mean to define a function as an integral? So we'll go over that in class, and then you'll be very well versed in the fundamental theorem of calculus. But this concludes the video portion of the notes.